Okay, in this lecture we are going to continue our 1D programming assignment. We had stopped at the assembly of the element equations, then application of the boundary conditions and the point load for the one-dimensional problem. Now we had raised a question of how to solve the resulting system that we had, which is of the form Ku is equal to F. Okay, and K was of dimension Nn DOFs by Nn DOFs, and it was symmetric. So as we had mentioned in passing at the end of the last lecture, there are two types of solvers which are basically popular in engineering analysis, especially when we use FEM. One class of solvers is called the direct solvers, and the other class is called the iterative solvers. So the direct solvers work by direct elimination of the unknowns to get the solution, while the iterative solver, it works by first taking an initial guess of this u and then trying to correct the solution, add corrections to this initial guess to get to the solution of the problem. Each one has its own advantage, but for our case, for the system that we are interested in, let's look at only the direct solvers. And within this class of direct solvers, we'll look at an important category of Ldu decomposition based solvers. What do we mean by Ldu decomposition? Let's see this through an example. Okay, let's take this matrix problem, which is a 3 by 3 problem given by this kind of a system. You see, deliberately I have made the matrix A or the K here a non-symmetric. This is a general problem. So what do we do when we have to do Gauss elimination? Then we simply go and subtract. I want to eliminate first the x1 variable from the remaining two equations, not from the first one. So what do? I simply subtract twice the first equation from the second equation. Okay, so to do this job, I do this and I get this one. Then I subtract once the first equation from the third equation. So by doing that, I have reached this form where I have eliminated x1 from this equation and this equation, from the second and third equation. That is, the first variable is eliminated from all the remaining equations. This is how, if you remember, the Gauss elimination is done. Okay. Now once we have eliminated x1 from the remaining two equations, then what do? We want to eliminate x2 from the third equation. So we are going downwards. From the second equation now, we take this diagonal, okay, and we would like to eliminate everything under this diagonal. Like in the first equation, we eliminated everything under the first diagonal. Okay. These diagonal elements are called the pivots, and we are going to simply eliminate this one from here. So how do I eliminate? By simply taking the second equation and subtracting it from the third one. So if I subtract the second equation from the third one, I'll get to this form: 1 2 1, 0 minus 2 minus 1, 0 0 3, x is 1 0 2. If you see this one, this has 0 entries in the part of the matrix below the diagonal. Okay. This type of a matrix where everything below the diagonal is 0 is called an upper triangular matrix. Okay, we'll call this by a name U. So now we want to know how through a series of operations can we take A and get U. We have done those operations. How can we write these operations in terms of matrix manipulations? So if you see what we had done, if we go back here, if we go back, so the first operation that we did was we took twice the first equation and subtracted it from the second one. Okay, so this operation I would like to write through a matrix, that I leave the first equation unchanged. Okay, I subtract twice the first equation from the second one. I do not do anything with the third one here, and I am leaving the third one fixed. This, if I multiply it with A, does the same job as subtracting twice the first equation from the second one of the matrix A. This one I am going to call with a name matrix D1. Similarly, if I go and look at the second part here, to eliminate x1 from the third equation, I take once the first equation, that is the first equation itself, and subtract it from the third equation. So how do I do this part? So this part will be given by a matrix. So I have the first equation which remains unchanged. Now I am doing nothing to the current second equation, so it remains unchanged, and I subtract once the first equation from the third one. You see, this is the subtraction process. This I am going to call as a matrix D2. Okay. Similarly, the third part was we took, so after we have done this, we have a resultant modified matrix A. Okay, matrix A is this matrix A. Okay, now what do? I go and take the second equation and subtract it from the third equation. So how do I write that? So now that this subtraction process can be written in the form, I leave the first equation unchanged, I leave the second equation unchanged, and in the third equation I am going to subtract the second one from it. So I take the third equation, from it subtract the second one. This is the process of doing this job, and this is given by this matrix D3. So in terms of these three matrices, now can I write U? Yes, I can. So what happens is, if I take my matrix A, first I operate on it with the matrix D1, that is the first subtraction of twice the first row from the second row. Then I do the second operation D2, that is subtraction of the first row from the third row, and then I do the third operation D3, subtraction of the second row from the third row. This job should give me the upper triangular form U. Okay. So if I want to now write A in terms of U is equal to, I will take the inverse of this set. The inverse of this will be D1 inverse into D2 inverse into D3 inverse into U. Okay. Now the finding the inverses of these matrices is very simple. So let us see how simple. This quantity I am going to call by a name. So I am subtracting this quantity from the, essentially it tells me by how much amount I multiply the first equation to subtract from the second one. This one I am going to call L21. Similarly, this quantity I am going to call as L31. Okay, and this quantity I am going to call as L32. So it tells me from the third equation, this is the amount by which I multiply the second equation and subtract. Okay, it turns out that if I look at D1 inverse, it is quite simple. D1 inverse will remain 1 0 0. We had subtracted twice the first equation from the second, so now I will simply have L21 1 0 0 0 1. So what I have done here, I have taken D1 and simply taken this part which corresponds to the subtraction and taken the negative of that, put it there back into the matrix, that becomes the inverse. So it is as simple as that. Similarly, D2 inverse will be 1 0 0 0 1 0. Here I will have L31 0 1. That is it. And the third one will be 1 0 0 0 1 0 0 L32 1. So finding the inverses of these matrices D1, D2, D3 is very easy once I know what is the operation through which I came to this form. Okay, you see that these matrices have a nice property, that these are only concentrated in the lower triangular part of the matrix, that is everything above the diagonal, now above the diagonal is 0, everything below the diagonal is non-zero. So the product of these two things, or these three things, will be the matrix L, which will have ones on the diagonals L21 in the off diagonal here, L31 in the off diagonal here, L32 in the off diagonal here, 1 here. You see what has happened? Now I have obtained a lower triangular matrix, and you see that the diagonals are all 1. This is a beautiful property of this matrix L. So now I can write the matrix A as a lower triangular matrix L into an upper triangular matrix U. Okay, let me get back and look at what was U. If you see U, the diagonal entries of U are not 0. So we can make, by a suitable modification, the diagonal entries of U also 0. How? How can we do that? So we can now say matrix U is equal to U11 0 0 0 U22 0 0 0 U33 into 1 U12 by U11 U13 by U11. Okay, here I'll have 0. Okay, here 1 u 2 3 by u 2 2 0 0 1. This I am going to call a diagonal matrix D. You see that what I have done is I have simply taken the diagonal entries and written it in a diagonal form here, and if I now multiply I should get back my u. This matrix is called, I am going to call it as u bar. So now I can write A as equal to L d u bar. So this is called the Ldu decomposition of A. Ldu decomposition of A. Okay. This is something that we can also do. Now let us get back. What is the advantage of this? Now even u bar has 1 on the diagonals. Okay. So before we go ahead, now you see how is this going to be advantageous, this decomposition. If I have Ax is equal to B, now instead of A I write L u. Now I will call y is equal to u into x. Okay, so implies we will have L y is equal to B. Okay, so here we have the lower triangular matrix into y is equal to B. Solving for y is very easy because here it is explicit, we do not have to do any elimination explicitly. So we first start with the first term, find y1, put that into the second equation, find y2 and so on. So this one, solving this is very easy. Once I have obtained y, then I will obtain x as ux is equal to y. So instead of operating with A, now we can explicitly operate with the L and the U. Okay. Now this makes life very simple because I can, if I have a stiffness matrix, I want to change the loads applied on the structure keeping the boundary conditions and the material fixed, okay, then my stiffness matrix is going to remain the same. Now as the load is changing, my load vector, which will be this side, is going to change. When the load vector changes, then I do not have to eliminate A, do a Gauss elimination on A all the time. I can have the L and U in store and simply take the new load vector, operate on it with the L and U, and I get a solution. So that is something we would like to have. Okay, let me now get back to my Ldu decomposition. So we had said A is equal to L d u bar. This turns out to be unique. There is only one such decomposition which is present. That is, if I have another decomposition and that decomposition equals A, then each of these terms have to be equal. Okay. Now you see something very interesting. When A is symmetric, then A is equal to A transpose due to symmetry. This is equal to u bar transpose d L transpose, but we know that there is a unique decomposition of A. So we know that for a symmetric matrix, u bar transpose is equal to L and L bar transpose is equal to u bar. Okay, which is consistent. So then for these cases, for symmetric matrices, the decomposition becomes very simple. It becomes L d L transpose. Now this we can write as is equal to L d to the power of half into L d to the power half transpose. Okay. So, I take this part, take the transpose of that, multiply the two, I get this decomposition for A being symmetric. This decomposition is called Cholesky decomposition. So, what I would like is for you now to take this information about what this Ldu decomposition based solver is going to do and take a commercial version of this solver which is available in various places, like again you can go to netlib.org, okay, get the symmetric form because your matrix is symmetric, that is LDL decomposition, okay, of the source code for this decomposition in whichever form you want, Fortran, C or C++, or you can go to the book. This is a fantastic book on numerical analysis, numerical recipes. This is available in various versions. It is for Fortran, C and C++. On all these versions, this book is available. Now, in those numerical recipes, source codes are given. So, the programs are given. So, you can take the program from there for the Ldu decomposition. I think it comes under the name LUDCMP. So, I would recommend use of this book to find the source codes. Okay. So, once we have now obtained the solver, which is the Ldu decomposition based, certainly for us, we know our stiffness matrix is going to be banded in nature. That is, there is only going to be a certain number of elements on either side of the main diagonal which are going to be non-zero, everything else is 0. In that case, I can further reduce my cost of doing the elimination or finding the solution. So, you can find in these books the banded solvers. So, essentially what happens when you have this kind of a property, that your matrix is sparse, okay, that is there are a lot of zeros in the matrix, then I can simply store only the part which is non-zero. Okay. So, there are these solvers which take advantage of that, and the elimination also I will do using that information. So, the cost of computation then comes down. This also one can use the banded solvers. Okay. So, now we have solved, we have obtained a solution, that is we have obtained these degrees of freedom u, okay, which implies that I should be able to now get the finite element solution anywhere in the domain, specifically in an element K. I can get the solution in terms of the master element coordinates. Okay. How? UFE at any point x is equal to, in the element K, is equal to sigma I is equal to 1 to P plus 1, which is end off for the element U I G, okay, N I hat, okay, where psi corresponds to the x that we have taken. Now, what is IG? IG, if you remember, is nothing but IEL DOFs K comma I. So, for the kth element, the ith node. Okay, so it's very easy to construct the solution in each element, so I can do it piece by piece. And also now DUFE dx in the element k is equal to nothing but sigma I is equal to 1 to p plus 1 uig dni hat d psi whole thing into d psi dx, which is 2 by hk. So this will give me the derivative of the finite element solution at any point in the element. Okay. Now you see that these are the degrees of freedom which we have already solved for. This we will obtain from the shape function routine. This I will get from my solver. This will come from the shape. Okay, and I am done. Okay. So give me any point. Now as far as plotting is concerned, what we can do is take the master element, divide it into some number of subdivisions. So I say psi 1 is equal to minus 1, this is my psi 2, psi 3, so on. This becomes psi n plus 1 is equal to plus 1. I can find the size. At these size I will find the solution. How? By calling the shape function routine, telling it to give me the shape functions and the derivatives, and using that to construct UFE at the point psi I. These I can output, so I can loop element by element, that is I go over the various elements in the domain, element 1, 2, 3 and 4, and for each element put this uniformly distributed set of points, output the value of the displacement and the derivatives at this point. So let us say I get something like this as my output. Okay. So now I can connect these by a line to get a plot of what my finite element solution will look over the whole domain. This is it. So as far as plotting is concerned, I can output the values of the finite element solution at these points, connect them by a curve, and I am done. Similarly, I can do the same thing for the derivative. Now, what do we see? We see that the UFE is very good at the nodes. What are the nodes? Nodes here we mean as the extremities of the elements. These are our nodes. It is very good. What do we mean by very good? It is very close to the exact value if I had an access to that at these points. Okay. There is a rate of convergence for these. Essentially for such problems that we have taken, it goes as order h to the power of 2p. That is the error between the finite element solution and the exact solution at this point. Okay. Further, if I have this, then I can see that essentially if I plot the difference between the exact solution, if I had access to it, and the finite element solution in an element, it will essentially look like this. So this is u minus u fe. Okay. Now imagine that my size of the element tends to 0, that is I am shrinking the size of the element. Then I can show that this is essentially equal to some constant a p plus 1 n hat p plus 2, sorry it should be a p plus 2 n hat p plus 2, that is it is essentially given by the next higher bubble function. So I have taken all the bubble functions of order p. Now this one corresponds to the bubble function of order p plus 1. Okay. Now if we see that somehow from here, I am not doing it explicitly. Essentially can be written in terms of what we had given as the Legendre polynomials of order p. So, if I take the derivative, this is all I am doing this in the master element. If I take the derivative of this finite element solution in the master element, the error in the finite element solution, it will essentially be of dominated by this term, which is the term corresponding to the pth order Legendre polynomial. Now, if this guy has to be 0, what do we mean by this guy being 0? So, this is 0 d psi of u minus ufe as hk tends to 0, it tends to 0 at where? At the points which are the roots of the Legendre polynomial of degree p. It is as simple as this. Okay. So, let us take an example. If I have taken linear approximation, okay, if I have taken linear approximation, this derivative, see if I have to find ddx of u minus ufe, I will simply multiply it by 2 by hk. So, that is not a big problem. So, wherever this is 0, my actual derivative is also going to be 0. Okay. So, if I take the linear approximation, that is p equal to 1, then by what we have here, the derivative in the finite element solution should be exact, should tend to be exact at which point? At the root of the first Legendre polynomial. The first Legendre polynomial is some constant into psi. So, it should vanish at psi equal to 0. So, you will see that in fact that is true, that the derivative, the error in the derivative is 0 essentially at the center of the element. Okay. Similarly, if I go to p equal to 2, I will see that the derivative vanishes at the two roots of p2. Now, what are these roots of p1 and p2? These are nothing but the Gauss points corresponding to the 1 point rule, the integration points. This is at the points corresponding to the 2 point rule. So, I can essentially, if I have obtained my solution using a p order approximation, then I go to the p order or p point rule and find those points corresponding to the p point rule. At those points, I know that my finite element solution, the derivative of it, is going to be very good. These points are called superconvergence points. Okay, so if I have obtained superconvergence points, so I should, if you look at this, there is another thing you should look, that at the nodes, that is at the extremities of the element, my derivative obtained from the finite element solution is the worst. It is the worst that I can get. In fact, I should try not to use that information. So, how can I use the information about these good values of the derivative of the finite element solution to obtain a better approximation of the derivative? Okay, by some post processing. So, what we are actually now doing with the previous transparency also, we had done that thing that, okay, that here also we had said the plotting, we are actually in the regime of the post processor. So, once the solution is obtained, we are talking of how best to interpret our data, to represent our data, and how best to extract something better from it. So, I would like here to get a better value of du star dx from my dufe dx. Okay. I know that I can use the values of the finite element solution, the derivative of it, at these points which correspond to the roots of the Legendre polynomial of order p, which are nothing but the p point integration rule. So, if I have given these points, let me call these points, so superconvergence points, convergence of derivative of du fe dx at roots of the Legendre polynomial of order p, where p is the order of approximation which corresponds to p point integration rule. So, I already have this information stored with me. Where are these points? So, I simply take these points and I will call them as points psi I superconvergence. Okay. Now, I going from 1 to p. So, given these points, now if I go to the elements, so by mapping back from the master to the physical element, I will have some points in each of the elements where my the derivative of the finite element solution is going to be good. So, if I plot these derivatives in the elements, you will see they will do like this, and there will be a jump in the value here at the interface. Okay, so derivative will do this. Now, this is something bad. I do not want, so this is d dx of u minus ufe, where u is the exact solution. So, here I am talking of the derivative of the error. Okay, and we want this to be essentially the straight line 0. I do not want the derivative of the error to be big anywhere. Okay. Further, at the interfaces, I get a jump in the derivative of the finite element solution, which is something I do not want physically, because it leads to a jump in the axial force that we obtain. Okay. So, how best can we now use this information about these points to create a better derivative information? So, the simplest possible way is the following. Let us say this is my element k, so this is its neighbors k minus 1 and k plus 1. Okay. Let us say here I am doing the 1 point rule, but you can have the various things. This is corresponding to x1 k superconvergence, this is x2 k superconvergence, x, my mistake, it is x1 k, here it will be k minus 1, here it will be k plus 1. So, x1 k minus 1 superconvergence, x1 k superconvergence, here it becomes x1 k plus 1 superconvergence. So, these are the mapped physical points corresponding to the superconvergence points in these elements. Let us say I have taken linear approximation for the time being. Okay. Now, at these points I know my derivative is going to be good. So, let us say my derivative here is this, derivative here is this, derivative here is this. Okay. So, what I am going to do is to obtain du star dx in element k. I am going to, because I have used linear approximation, I am going to now represent du star dx by a linear in this element. So, I am going to represent it as a0 plus a1 x in this element, and I also extend it by the same thing in the neighbors, that is the k minus 1 element and k plus 1. Now I would like to get these coefficients such that I hope that it is going to be a better derivative information in this element, okay, than what we had out of dufe dx. So I would like to obtain essentially using this information the straight line fit, and I hope that this straight line fit is essentially equal to du dx. Now how do I construct this straight line fit? So I take for the element k, remember I am doing it for the element k, so I have to do it for each element separately. Find these coefficients a0, a1, from there construct the value of the variation of du star dx in the element k. So to do that, what I do is, again I take this neighborhood, this k, k minus 1, k plus 1, okay. What I am going to do is, I am going to define this functional, okay, as half sum over, okay, x1 I s, okay, sorry, as sum over all the i's, I is equal to 1 to 3, 3 into, actually it should be 3p, okay, of dufe dx evaluated at the point x, for us p is equal to 1, I s minus du star dx evaluated at the point x1 I s whole squared. So what am I doing? I am taking, this guy is given by a0 plus a1x. So I am taking these values of the x from the superconvergence points for the neighbors, putting it here, I am doing this discrete sum. This is my functional j, and I am looking for the coefficients a0 and a1 which minimize. So find a0, a1 such that j is minimized. J, I would say it's defined for the element k. So this definition I have to do for any generic element k. Okay, so I have to go from the first element to the second one to the third one. I'll find these coefficients a0, a1 corresponding to the element. From there I can construct du star dx at the element level. Now what happens at the various places? If I have an element at the boundary, that is the first element, so in this case I do not have the 0th element, so I will only take this neighborhood. For the last element, again I will take the n minus 1th element and the nth element. So this is NELEM and this is NELEM minus 1. And this is how I am going to construct these so called recovered coefficients. Now when I piece them together, I will see that essentially my du star dx will look like a piecewise linear. Okay. Now at a material interface, if I am at a material interface, so if this is my element, which is, this is my material interface, okay, I am sitting at the material interface, then I do not take the neighbor. So if this is my element k, I do not take the k plus 1 neighbor because it is lying on the, in the different material. So I will only take the neighbors from the same material neighborhood. Okay. This is how we can construct the recovered du star dx in each element k. This is called the patch recovery method. Okay. And this indeed gives us the values of the derivatives which are very good. So if we do this kind of a post processing, we can construct very good recovered derivatives without doing any extra computation. The computation here is minimal and it is done at the element level. So I'll do for each element separately. So out of this, out of what I did here, I'll get a system of equations in terms of A0, A1 up to AP. Okay. So I'll solve that system of equation for the element. I have to solve it for all the elements separately, one by one, and I have constructed the du star dx information for all the elements. Now this one is said to be a super convergent recovery method. Okay. There is another version of it where I can actually modify J to have here EA at the point x 1 I comma s. Okay, here I have taken 1, but in our sum we should have over all these integration points in the 3 elements which form the neighborhood or the superconvergence points. Okay. Here also I will have EA at x1 I comma s. If I add this, you see this is called, this is another way, an alternative definition of getting these superconvergent recoveries. Okay, especially when my EA is non-uniform but not transitioning. Okay, it is simply if it's a tapered beam, for example, then this will do the job. Okay, now we have done these recoveries. Certain things. So once we have done this, our post processing has also been completed. So after we have done all this, we have written a program. How do we check our program? We check it using so-called patch tests. Patch tests or benchmark tests. What is the basic idea in all these is that we take problems for which we can get the exact solution. And then we go and try to solve these problems and we see whether our finite element solution is close to the exact solution. It should not be too far away. If it is too far away, there is some problem. In fact, in the patch test, we can construct, at least for the case k naught equal to 0, let us say, EA is equal to constant. If we take our fx is equal to 1 or x squared, we know our exact solution in this case will be of the type x squared by 2. It's a polynomial. Okay, here it will be x cubed by 3 and here it will be x to the 4 by 4 plus some constants. So I know that in these cases when k naught is equal to 0, EA is equal to c, taking either this as my load or this as my load or this as my load, correspondingly I will get the quadratic, the cubic and the fourth order solution. Then what can we do? We can simply take for these solutions, let us say I have taken fx equal to 1, I will take p equal to 2, the quadratic approximation, and with this quadratic approximation I should get the exact solution to the problem back. Okay. Similarly, if I take p equal to 3 and take fx is equal to x, I should get ufe is equal to u exact. Okay. And for p equal to 4, I do this. If somehow my code does not give me the finite element solution equal to the exact solution, then there has to be a bug in whatever we have done. So now you have to go back and debug your program and set it right, so that till at least the machine precision that is specified, generally we do double precision calculations, my numbers match with the exact solution. So with this we have come to the end of the one-dimensional programming assignment, and with all these tools given we can develop the one-dimension code. Now what I have tried to do in this exercise is try to give you a feel of what will be coming or needed in the 2 and 3 dimensions. Essentially the data structures that we have constructed here, the kind of procedures we have followed here will carry over almost unaltered into the 2 and 3 dimensional cases. Now it is for you to write the program, test it for these patch tests or for benchmark tests for which you can construct the exact solutions, and then use it for other problems for which you would like to get a solution, for which getting the exact solution is difficult. Thank you.